All right, hey everyone. My name is Dirk Colbury. You can call me Dirk. I'm in the computational math, science, and engineering department. Any CMSE students in here? Raise your hand. Woo. I'm also the director of user support for the Institute for Cyber-Enabled Research, which is what I'm here for you today. I'm also happen to be the advisor to the club, one of the advisors to the club, so I'm an easy ask, and I come in periodically and talk to y'all. Other thing is I am teaching the data science capstone for all the data science majors in engineering. So if you're planning to take it next semester, you will see a lot of me, and I'm sorry. So today I wanted to talk to you about AI specifically, but our high performance computing center here. And just to start it all off, you all are allowed to use the HPC. You can use it, especially with your AI club projects. I am happy to get you accounts and get you on. It's not easy person computing. It is high performance computing, but we try to make it easy to get on and use, and you'll learn a lot. So I recommend you give it a try. And it costs the AI club absolutely nothing for you to have an account. It costs you $50 in my pocket. No, it doesn't. This was working. I turned it off and back on. I think it fell asleep. So today I'm going to talk to you a little bit about science. I just like starting off my talks like this. And then in the olden days when science was first aroused, it was the thinking person, usually the man, that sat around because they were rich and thought about how the world worked. And they came up with this philosophy we still use today, right? You'd come up with a theory for how the world worked, and then you would do experiments and test your theory. That's a pretty solid model for science. We've used it for years. And at some point, though, the theories got so complex, they had to invent something. And what they did is they invented math, right? Math are just more complex theories, models of how the world works. We can model it using math. And that really helped us come up with better theories. And then we would use, but models only get us so far. There are some models, some things you can't model with just math. I know that's surprising. But there are a lot of things we just can't get at all the aspects. They're too chaotic, they're too complex for math alone. So we go into simulation. Oops, I went the wrong way. This is the first computer on MSU campus. It was in 1957. It was called Mystic. This one was fascinating. You couldn't just go to your local computer store and buy memory and stuff. You actually had to make it. They would buy these little disks, circular magnets, and they would wrap them with wire, and that was the literal memory that was used. And they made this on campus here by hiring undergraduates to wrap a bunch of wire. I wasn't there. This is before my time. But it was pretty amazing. The computers in your pocket are many thousand times more powerful than Mystic. But even at the time, it was pretty powerful. We could do a lot of science on Mystic, or I say we. MSU did a lot of science on Mystic that was much more powerful than what they could do with their math by themselves. And that's been true for a while. Simulations get more complex. They're getting huge. Brian O'Shea, who's a faculty here on campus, gave me this picture. This is a part of a simulation of the formation of the universe from the Big Bang forward. It's a galaxy formation. I don't know what it shows. But think of the scale that it requires to make a simulation of the Big Bang forward. It's pretty darn impressive. And the fact that he's doing it even on a level is pretty darn impressive. And what that does is that takes major computation. On the experiment side, we started off with basic observations. We would actually hire artists. I say we. Again, I'm not a scientist back in the olden days. But they would hire artists, or actually a lot of artists became scientists because the observations needed to be recorded, and the best way to record it was to draw as accurate pictures as you could. But as things moved on, we learned that we could generate measurements instead of having to write it down. We could build tools to answer scientific questions. This is a good example. Back in the olden days, there was a political upheaval. There were the grounders and the not grounders, I'll say. There were some people that believed at least one hoof of a horse when it's running is always on the ground. They were the grounders. Okay. And then basically all of science said, no, that's a bunch of horse pucky. All four hooves leave the ground when a horse gallops. And the science, they had lots of scientific evidence that showed this. But then there were still these grounders out there. I don't know if you can run a parallel to today. You can make up your own scientific, where science is 100% behind something or 99.9% behind something. But then this experiment was done where a guy invented a high-speed camera. Actually, there's many cameras. And then he ran the horse by the cameras. And he was able to show, look, I took a picture. There's a point at which all four hooves are off the ground. And this evidence solved the problem. No one believed it. There were no grounders anymore. I wish that would happen today. But that data solved the problem. And what we're seeing in science is that there's just more data. We can do genome sequencing. We can do large-scale image analysis. Data is everywhere. All right? And so now we don't only need computers for simulation. We need computers just to analyze the data that we have. And the data becomes the science. And this is the world we're in now. And so in the 70s, this was actually proposed, so it's not an old concept, that computation is the third pillar of science. Okay, so you have your theory, you have your experimentation, but then you have this idea of computation. I actually don't like that. It's not an equal thing. I actually say modern science, the foundation of modern science is computation. You cannot find a modern scientist that doesn't use computation in their research. Now, it might not be big computation. It might just be using a laptop to write their journal articles and submitting it online. But everybody's using computation. It's fundamental to the way we do science. If you need more than your laptop, you need something else. And a lot of science is that way. And that's where ICER comes in. We are the supercomputers on campus. And there's my advertisement. All right, so what can you do with that? ICER's been around since, like I said, well, not ICER. Large computation has been around on campus in 1957. Over the years, the way you used to do it is you would buy a big computer, you'd put it in a room somewhere, and it'd fill the room. And then all the scientists would run stuff on it, and then that computer would get old and old and old and start failing, and so then they would scrap that computer, buy another big computer. And that's just how we did big scale computer. But in around 2004, we changed the model. We said, okay, instead of buying a big computer, waiting till it's done and scrapping it, we use a different model. And I don't know, has anybody ever heard of Theseus's paradox? Right? The idea of Theseus's paradox, and you can read the thing if you want, but you have a boat, Theseus' boat, and some of the boards rot out on it, so you replace them. Some of the different boards rot out, you replace them. After year, you're replacing all the parts. At some point, you've replaced every part on the boat. Is it still Theseus' boat? Well, I don't care. It's a philosophical question. It doesn't matter. But that's exactly what we do at the HBC. We bought a computer in 2004, and the computer we use today is the same basic computer, except we've changed everything. We kept the accounts the same, essentially, but we've even changed the building where the computer is stored. And we did that while the computer was running. So that's Theseus's paradox. And how do you do this? Well, we do something called a commodity cluster. And the idea is very simple. You have these cores. These are the chips in your laptop. How many cores do you guys have nowadays? 8, 16. This picture is 4 because that's an old picture. Anyways, you have some chips on your computer. You might have more than one chip on a computer. Some computers can have more than one. Ours usually do. So we call those sockets. So each socket can have a chip in it. Each chip can have multiple cores in it. And then we put those in a computer very similar to your laptop, maybe a desktop, because it has more than one socket. It has RAM. It might have a disk in it. It's not much different from a speed point of view than what you would have on your top-end computer. Okay? But then what you do is you pile a bunch of those nodes into something called a chassis. You put more than one into chassis. And then you slam a bunch of those chassis into a rack. Still, we're not doing, any one of these computers is not more impressive than what you could buy at Best Buy or something. No one buys at Best Buy anymore. Buy online. Pick your store. What makes this a supercomputer is the high-speed network. We have a really, really high-speed network, special cards in each one, that is much higher than the network going into your home that's so fast that the limiting factor on it is the speed of light. If we could make light faster, we could make our computers faster. And because of that, these computers have to be close together. Once you get past 50 feet from each other, the light is so slow that it slows the computer down. Okay? I'm not kidding. So that's why we have to pack them all close together into a room. The other thing is it's really hard to cool these because they generate a lot of heat. But this is what makes it a supercomputer. And so we buy a high-speed network and we connect all these commodity computers together with a high-speed network. The other thing we do, which I think is really important to this group, is we also throw in something called a bunch of accelerator cards. You'll be familiar with them. They also called, the most common one is called a GPU. So you slam in, this is your desktop. Now we put in not only one, not two, but maybe up to 8 of the highest end GPU cards you can find in one node, and then we put a bunch of those nodes into a rack and we connect it with a high-speed network. That's what makes it a supercomputer. And what's neat about that is over the years, we just keep upgrading. Right? When we first bought it back in 2005, we bought a bunch of AMD cores, put them in a bunch of nodes in, added them. Then 2007, we bought a bunch of Intel cores. We put them right next to the AMD core, connected them to the same high-speed network. And then we kept doing that every couple of years. We'd buy more. And then after a while, about 6 to 8 years after a computer had been bought, it starts to die, so we take it out. But by then, we have a bunch of new stuff in there. And at some point along the way, we upgrade the network. And at some point along the way, we upgrade everything. And like I said, even to the point of we're not even in the same building before. We've updated the operating system this year. That's how we build a commodity cluster. This is the heart and soul of the High Performance Computing Center. If you all want to work on it, you will be working on these computers. And it's in a data center. I got a picture. So what do we do on these things? Well, like I said, there are 3 major cases of problems that we try to solve on these things. One I call boundary simulations. That is that formulation of the universe from the Big Bang forward. What you do is you take the real world and you make a simulated real world. You cut it up into little boxes. And you do your little calculations in your little boxes. This can be fluid dynamics, finite element analysis, all these things where you just take a small piece of the world, you do a little bit of calculation, and then you tell what's next to you what you did, and then they slurp in the differences, and then we do a little bit of calculation, and then we slurp in the differences, and we do a little bit of calculation. These are also called large-scale partial differential equation solvers, if you want to know. You can do a lot of amazing simulations. This is what I call traditional high-performance computing. It's what we originally made the system for. But we do also a ton of data analysis. That's where the GPUs often succeed, although you can use GPUs to do boundary simulations as well. Large-scale data analysis, lots of AI going on in there. And then the third thing we do, which is sort of related, but it's slightly different, is this concept of search. You're trying to optimize something, you're trying to find a solution, or you're trying to find, usually a solution. You're trying to either minimize a function or maximize a function. And there's no analytical solution to that. And so you basically try all possible inputs until you find the minimum or the maximum. And we do a lot of search. There's things like genetic search and Monte Carlo search and a bunch of different other ones, if you've heard of them. But most of the problems we solve on the HPC fall into those 3 categories. All right. And it's free. It's paid for by the university to advance science and education on campus. It's not really free. We pay a crazy ton of money for this. Most of that money is coming from grants coming into the university. Every grant that comes in takes approximately 52% tax that goes to the university. They use that tax, like if I get $1 million grant, I'm only going to see half of that, basically. And that sounds terrible, but that's what pays for the lights, it pays for my office, it pays for the floors to be clean, and it pays for the High Performance Computing Center. And the power. All right. I'm going to skip that. We have about 56,000 cores on the current computer. So you had, what, 8, 16? We have 56,000. There are about 1,000 nodes, 614 GPUs. Total memory is about 317 terabytes of RAM. We can store about 8 petabytes of data. And the theoretical peak performance, if you're into this kind of thing, is about 3.9 petaflops. It's a big computer. It's a friggin' big computer. Now, rarely does anybody use the whole thing. Right. This is a theoretical max. No one's ever run the whole. We've run some benchmarks, but that doesn't really count. No one's doing science at this rate. Although Brian O'Shea, Simulating the Universe, would love to do it, and he's actually the director, so he probably could get away with it, but he won't because of politics. Anyway, so that's the supercomputer. Here's how you access it, right? You have your laptop. It's a cloud system, right? You go through the internet, and you connect, usually using something called SSH, Secure Shell, if you're familiar with that. We also have this thing called ondemand.hbcc.msu.edu, which is a web-based interface. I actually prefer this nowadays. I like it. It's really nice. It gives you you don't have to install anything on your laptop to use it. These we call gateway machines. They're not powerful. They're just VMs that we maintain, virtual machines. But that gets you in. That gets you past our security. You'll have to use your MSU login and password, although you need an account first. I'll explain that in a second. Once you're here, you can log into these things called developer nodes. We call them dev nodes. And for every hardware type we currently have in the cluster, we usually have 1 or 2 dev nodes available. So we have dev AMD20 V100. What does that mean? That's a development node that runs a processor called an AMD. If you're familiar, it's either AMD or Intel usually. This was purchased in 2020, so you get an idea how old it is. And it has a GPU on it, which is a V100, if you're familiar with that. And so we have a cluster of these, but we put one out to the side, and you can go from one of these nodes into one of these nodes, and you can do whatever you want. These are shared by lots of people. Sometimes they're slow, sometimes they're fast. You're kind of limited to 2 hours on any one dev node, but that's 2 hours of typing. If you're just sitting there doing nothing, it doesn't count. It's 2 hours of computation, is what it is. But it's meant for you to develop your code. They're identical to the cluster nodes. It's just you can access the command line and do whatever you want with them. They're pretty fun. But once you get your basic workflow working, the real secret to the HPC is a batch system. So what you do is you wrap up what you want to do in a batch job, which says how many resources you want to use, how long you want to use it, and you put that in a script along with the commands you want to run. And then you give it to the scheduler, and the scheduler looks at the cluster and tries to find where those resources are located, and will give you dedicated access to those resources for the time you request it. And the cluster is big, right? So there's a lot of resources. There's a lot of places you can run. And that's the basic idea behind how the HPC works. You do your basic day-to-day work on the dev node, but when you're ready to really run that big learning algorithm or fine-tune some LLM or something like that, usually you would submit it to the job as a batch job. And then you have to wait for it to start. It's usually not that long. But it could start in the middle of the night or whatever, and then when it's done, the output will just be given to you. That's sort of how it works. All right. Before I move on to that, what questions do you have about the HPC? Anybody excited by this? Yeah, go for it. Actually, it's funny you said that. Tours have been limited because it's a high secure facility. It actually stores all of campus's private information. However, we got approval to do a tour as long as everybody who's on the tour is sponsored by a staff member, and they have to fill out a background check. So it's kind of a pain, but we can do it for small groups. This might be a little much, but we could do it for small groups. So maybe as a prize for winning or something. I don't know. Yeah, go for it.
What's stopping a student from doing something like this?
MSU's IT agreement. You will be kicked out. We actually knew. We've kicked people out, and it's been pretty harsh. We're not idiots. We know what you're doing. We don't monitor specifically, but some people have done some really stupid stuff. If it's related to research, it's allowed. We haven't had anybody do Bitcoin mining research, but they would want to register it with us. But if they're legitimately doing research on Bitcoin mining, that's legitimate research from the university's point of view. I'm happy to do it. Yeah.
The data for like the program on in the data center, or do you host it locally?
Yeah, so everybody gets a home drive. It usually is about 50 gigabytes. And then you get something called scratch space, which you can get up to, I think, 5 terabytes. The scratch space is not backed up, and it will go away every 45 days. It's meant to be staging. So you put your data in that you want to use for training, you run your training, and then you get rid of it off of scratch. And you put the results, the things you want to keep in your 50 gig home drive. There are other ways to do that. Research groups can get more space, and there's other things. So basically, that's how it works. Yeah.
We use this for our personal projects as well, something related to school research.
It has to be related to your education as a student. If it's a personal project that is part of your personal education, it's probably not. If it's a company that you work for and you're bringing their data and their work, probably not. You have to follow MSU IT policies. Like with any MSU computers, we have policies. They're very explicit. But we're pretty flexible too. If you're just noodling around on a project for your own personal learning, that's absolutely okay. And you, as a student, you should all know this, as a student here at MSU, you own your intellectual property for all the work you do. That is rare. Most universities take students' intellectual property. That means if you invented something in a classroom, the university would own it. MSU specifically does not do that. If you invent something in the classroom, you own it. I just want to say that because it's important. I'm proud of MSU. Other questions? Yeah, go for it. I have a slide on that. Yeah. So the secret, I'll put this on the end, but the secret to getting you an account is to email me, and I'll give you the my email address. You can also contact anybody on the board. They know my email. And just send me a note, and I'll explain what to put in it, but basically say, hey, I want to do this project. Here's why. Will you sponsor me? And basically, I'm going to go to bat for you. And I'm happy to do it for anybody in here. But if you start Bitcoin mining without me knowing it, it's on my head, and I'll be kind of annoyed. Okay? So just be professional about it. Yeah. I don't remember. I think it's on the order of 50 gigabytes a second. That might be low. I think I'm a little old. I feel like that date is like 6 or 7 years out of it.
Still,
it's extremely fast. It is orders of magnitude faster than anything you're going to get into your, right, anything you're going to milk on a local nav. But like I said, these are very expensive networks, and the fiber that we use is very advanced. No, that's the internal communication between the nodes. We have a full bandwidth, multiple channels to the backbone that's at MSU, so we do get really good internet connection too if you want a web browser, stream some video, which is a weird thing to do. You'd be streaming a video on a computer in a cluster that then you're accessing through a portal that wouldn't handle the streaming. But yeah, you could, in theory. Other questions? Happy to answer. This is like my thing. Yeah, go for it.
So let's say the timeline for, say I have an idea and I want to email you for that, and then eventually I'm able to get access. Is there resources online? Because you mentioned it's not easy computing, right?
It depends. Oh, you are. You'll have no problem. But yeah, it is. It's Linux based. We have a full online documentation, which we work really hard at being good. We actually welcome feedback all the time. There's ways you can just click and it will go take you to a form, which immediately submits that to our issues list on our GitHub repo for our documentation. And we have a weekly meeting that reviews that and updates it. So we're pretty responsive. We also have a few open D2L classes, if you like that, with videos and stuff like that. They're free to anybody. There's links on the website. You basically can just learn HPC through D2L. Just because that's where the videos are. It works pretty well.
Sorry, I also wanted to ask, what OS do you guys use?
Right now? Oh, good question. Lots. All of them Linux. The infrastructure uses a variation on Alma Linux and CentOS, whatever, one of the versions, CentOS. We just upgraded all the compute nodes, basically the user-facing nodes, to Ubuntu. And if you're really interested, I'm actually writing a paper on why we chose Ubuntu. It was a very hard decision to pick an OS. But if you're an Ubuntu fan, it's not a hard decision. But honestly, it's a hard decision. Ubuntu is not a traditional HPC. We are actually one of the leading universities that are pushing and contributing back to the open source community to make Ubuntu more common on HPC. But we picked it for reasons mostly political, that CentOS's license is really terrible. That's what we used to be. I could get into that. I'm writing a paper.
I would love to.
Yeah.
Well, the paper's not done. But yeah, maybe if we have time. Did you have a question? Does someone have a question over here? No? Good questions. That was fun. Maybe we could get a little more. Ubuntu's good. It's not my favorite Linux flavor for my personal computer, but I'm a nerd. I recommend it to most people when they don't know anything about Linux.
You get the option to set up your own VM to like put your own like OS on it.
We have something called Singularity, which is a type of VM, but it doesn't give you root.
Okay.
We have to have actually very strict security.
Yeah, of course.
It can give you root light, and you can do things like put your own OS and crap on it.
Okay.
To me, that would be way more effort than needed because if you want to, go for it. But we won't then support that.
Ubuntu is perfect.
Yeah, it's fine. It works. And we actually have the old OS, which is CentOS 7, in a VM that people can just run. So if they have their workflow set up on the old system,
Okay.
I don't want them staying on the old system, but some people can't get it working whatever on Ubuntu, they can actually use the VM to run it on the old system. And in theory, they could run any OS they wanted, except Windows doesn't work at all. And Mac OS, BSD sort of works, but not really. You have to stick with Linux. Sorry, I'm getting into the weeds, but it's fun. Other questions? This is the AI Club, so I sort of wanted to talk about how we use this for AI. That is my area of specialization. I've been an AI expert since I started in robotics in around, this will really age me. I started my first robotics job in 1997. I worked for Fanuc Robotics, which is a big, they make big robots that assemble cars, basically. And I was a mechanical engineer back then, but I quickly went into their software development team, and I would help write some of these old school AI type engines. I went to grad school because I was really excited about robots, and the robots were stupid. And so I went to grad school into AI and machine learning in the early 2000s, and I've been doing variations on that ever since. Yeah, so let's talk about the hype curve. So right now, AI, all technology is on this hype curve. I don't know if you've heard it before, but I just want to show you what it looks like. This is a traditional hype curve. It has a peak here, a valley here, and it lets off. And just to give you what it means, LLMs, generative AI, is right here on the hype curve. We are at the top. The AI Club is golden. Right there at the top. And just as another example, I think, oops, wrong button. Blockchain. Bitcoin is down here on the hype curve. Just a few years ago, it was up here, and now it's down here. Now, the hype curve is measured not by an individual's opinion, but by a population in general. And they actually have ways to measure these things. And so right now, blockchain is down here. And then, oops, I didn't have it. Like, the internet is out here somewhere, right? In the 90s, when the internet was first, I was in the middle of it, and the big internet boom happened and all that stuff. It was here on the hype curve, and everybody lost all of their money. It was the end of the world, and then we came back. And now it's a perfectly good technology. Everybody uses it. It's very great. We're not as hyped as it was, but we all think it's pretty good. And just as a contrast, I like to show this curve. This is called the Dunning-Kruger effect. Anybody familiar with the Dunning-Kruger effect? Yeah. If you know what it is, you might be laughing inside. The Dunning-Kruger effect is an individual's response to knowledge. So our competence, based on time, how competent we are in a field, and our confidence that we're competent. So if you know a little bit about something, your confidence is high. And this is true if you're a PhD or not. Everybody has this problem. If you know a little bit about a topic, your confidence is really high. And then as you learn more and you become more competent, you become less confident. This is a well-studied thing. And you get into this. This is actually, grad students, the valley of despair happens in the middle of grad school. Because you realize, oh my gosh, what I'm doing is a bunch of BS. Sorry. That's normal. And then when you're the expert, you're up here. You have more confidence than the valley of despair, but you're not even close to the ignorant person who just has overconfidence. And the reason I like to show that is the similarity between these two graphs, right? This is an individual's response to knowledge. This is a population's response to knowledge. They're the same friggin' curve. And it's the same effect, it's just at scale, and it's easier to measure at scale. Basically, as we know a little bit as a population on a new technology, the hype gets often very high. As we learn more about a technology, we see all of its warts. We haven't quite hit that with the generative AI movement yet, but we will. It's going to happen. That's okay. You can still be an expert in AI and acknowledge that we're going to hit this at some point. And then we'll come out, and we will. Predicted right here, right now. It happens with all technology, so it's guaranteed to happen. How deep we go depends on a lot of things. Maybe it won't go as deep as blockchain. Mostly because a lot of people lost their money unintentionally or intentionally in blockchain. But bubbles will burst. And it's the effect of a population effect from an individual understanding. And so the more we know about a technology, the hope for me is the faster we'll get past this. And so it's really great that you're in the AI club. You're studying this stuff. You're getting to know it so that you will be best prepared to weather this dip. We're going to figure out what technology is going to last for a long time, and we're going to figure out what's the crap. Yeah?
So what in grad school do you exactly get out of the valley?
Well, let's have a talk. Group therapy. I have lots of talks on that, but that's a different talk. You will get out, but probably not till after you graduate. All right. Any questions about that? I just like that. I hope you like that. But let's talk about the nuts and bolts. On the HPC, we have a ton of software installed. We have hundreds of different software libraries already pre-installed. You don't have to do anything. We have a system called a module system. You just say module load PyTorch, and PyTorch is running. We have Jupyter. We have all kinds of great, wonderful things. They exist already on the HPC. They already are configured to best use our hardware, especially our GPUs. That is wonderful. I, as the AI guy at ICER, have been working on our mission plan for AI at the university as far as ICER is concerned. And we've been really looking, and let me just explain what that means. ICER's job is to accelerate research on campus. That's our job. We use computers to make research go faster. How we do that is varied. We do a lot of education because sometimes it's not the computer that's the slow part, it's the researcher who needs to understand the computer so they can understand what they need to do with it. We do a lot of education. But also we have to understand the workflows that the science uses. And right now, because we're so early on that hype curve, it's unclear how science can best use some of these newer AI technologies. Right? What can a social scientist do with an LLM? Potentially a lot, but we don't know what's good and what's bad. What can a physicist do with an LLM? Something else, different. How do they want to use it? Do they want to use RAGs? Do they want to use fine-tuning? Do they want to use ChatGPT Naval? Do they want to use things in a sandbox so that they can share their data? There's a lot of so they don't have to share their data. There's a lot of things going on, and so my team at ICER is trying to come up with workflows that researchers are using when they want to use these tools. Now, these tools are actually pretty straightforward. We have plenty of workflows, like I program in Keras and TensorFlow and PyTorch. I've done them all. And I don't have a favorite, even though there are better ones. They're all terrible, actually. That's actually my philosophy with all libraries. All operating systems are horrible. We just pick the least horrible. Depends on what you're doing. But yeah, same thing with these libraries. There's pros and cons to all of them. Honestly, newer ones tend to be better than older ones, but not always. But we install all of them because we don't know what workflows you're doing. Once I identify workflows that researchers want to do, I try to automate those workflows as much as I can for them. Try to help them get from, here's the research I want to do, give it to the HPC as quickly as possible. I don't want to do a lot of programming. I just want to do my analysis, get my results, get my paper, get my Nobel Prize. That's what researchers want. And our job at ICER is to try to help that. The way we do that is to try to study the workflows that they want to do and try to anticipate what we can do to save them time. Because the most valuable thing is not computer time, actually. The most valuable thing is researcher time. We want to get them from ideation to publication as quickly as possible. So what I've been doing is I've been making with my team some sandbox tools. We call, I don't know, you guys know LM Studio? Big fans of LM? I don't know. It's a pretty neat tool. It really lets you download models from Hugging Face, LLM models, and just play around with them. It works pretty well. It totally, one of the reasons I picked this one is it interacts with our GPUs perfectly. We have lots of different GPUs. This thing can properly detect which GPU it's running on and use it, which is not true with all the tools. I want automation. It has a full chat interface, so I can open up the user interface through something, through On Demand. I can download a Hugging Face model. We also have pre-existing models already downloaded. And you can just start chatting with them like you would ChatGPT. Why would you ever want to do that on the HPC? Well, our researchers have data that they can't upload to ChatGPT. They're not allowed to. And they need a sandbox. They want to try things, but they can't. And so we're trying to provide them a sandbox where they can play around and do those types of things. What's also neat about LM Studio, if you're comparing different models, open source models especially, you can set it up so that all models are loaded at the same time. You give them the same prompt. They all run at the same time, and you get to see the differences in results, which is just fun when you're playing around with models. I also have a similar interface through Olama, and we're trying to build these as apps that run on the HPC. So my hope is that we can get these workflows down so that you all or our researchers can just say, hey, I just want to play around with the latest Llama 8 billion model thing. I can't run it on my laptop. It just doesn't work. But I know I can run it on the HPC, but I have no idea how to do that. We're trying to lower those barriers so that you can just click on a button and say, run this with this many GPUs on this core, and then you'll have to wait because it's a scheduled system, but when you get it, then you can just play with it and see what it does. And we're getting really close to that. I can do it now, but it's not fully automated. So if you want to do that, you come see me, I can show you how to do it basically. But we're working on these fully automated workflows so that we're reducing the barrier to entry for our researchers who just want to try things. And they don't care. They're not nerds like us, right? They don't care which model they're using. They just want to see what it does and see if it will answer their research questions, which is a really hard thing. The other big workflow I've been working on lately is RAGs. There's a lot of researchers who want, and if you're not familiar with RAGs, Google it. I assume this group is. They want to be able to reference original source, so they've created a directory full of references. They want to run their LLM model on that directory and ask it questions and then refer back to the original source. RAGs are really good at that. We're trying to make it as easy as possible to run those types of workflows on the HPC. And the third workflow I'm working on is fine-tuning. That's a lot harder. It takes a little bit more specialization, but you can fine-tune these models to solve specific problems. You all know this, right? Maybe? I don't know. So, this is the, good. You need an account. We use your MSU net ID and password. You don't need a new password or a new net ID. But we have to have an account on the HPC for you first. And basically, we just add your net ID to the list, and then you have access. The trick is you need a sponsor. If you're doing a project with a faculty, any faculty, they can request it for you, and that's the appropriate way to go. So if you're working in a classroom setting and you're doing a classroom project with an instructor, ask your instructor to make the account. It's easy. It is required them to be an instructor, though. If you don't have an instructor, you can ask your faculty advisor if you don't have a faculty advisor, and you want to do it for a club, let's say the AI club, just to make one up. You can ask the advisor of the AI club. And whoever that advisor is, and it can actually be any of the advisors, but you can choose which one you want to pick. And then send them an email. What I want you to send is, what do you want to do and why? I actually have to document this, so please be expressive. If you want to noodle around, I don't mind. Just say I want to noodle around to learn X, Y, and Z. And noodling around is an official engineering term. It means goofing around. And then, as we move forward, I will get periodic emails, very often actually, saying, here are all the people you sponsored. Do you want to continue sponsoring them? My default is to just say no, which means those people will get an email saying your account has been disabled. It's not a big deal. Then you email me back saying, no, Dirk, I was still working. But if you send me updates about what you're doing, why, and ask me questions, I know you're active and I won't disable it. Any questions about that? You have the supercomputer at your fingertips. Yeah.
Remind us again, what is the timeline for reminding you?
They cancel accounts on the semesters usually. Honestly, they don't tend to do it in December. So it's supposed to be every semester. They tend to skip between the fall and spring. And so they'll do it at the end of spring semester, they'll do it at the end of summer, and they typically skip the end of fall just because it's in the middle of the school year.
It did basically 2 semesters worth.
You can get as many as you want as you're making progress. There are CPU limits. If you hit them, you have to request more. That actually is a bigger ask, because if you hit them, we're going to say, what the heck are you doing that you're using that much CPU time as a student? Some of our bigger labs absolutely hit them, but if you're doing it as smaller, we're going to ask you what the heck you're doing, and is it an effective use of MSU resources? Every hour you run on there is costing MSU money. It costs a lot of money to power these machines, and it costs a lot of money to cool them down. We run them at about 99% at all time. That's the scheduling system. It's always running, always churning, always. And so if you're running on the system, which we're allowing you to do, that means someone else is not running. Okay? And so we want you to run, we want you to learn, we want you to even try things and make mistakes. That's absolutely okay. That's part of the learning process. But if you're just, we have this phrase called submit and pray. Don't do that. Basically, we have people that will say, oh, I want this to run, so I'm going to submit 10,000 jobs and hope that one runs. And, 999 of them ran. Oh, yay. Well, they all gave me the same result, and I just wasted all that compute power. Submit and pray is a way to get your throughput higher. I'm not denying that. But it's just wasting resources. It's wasting CPU for other people, and it's wasting power. So don't do that. But I'll yell at you. Hopefully, if I'm your sponsor, I get to monitor how much of the resources you're using. In theory, I don't typically, but if it's really egregious, a report will come to me and say, hey, this person's doing something really weird. Yeah?
Break it in a way by messing with it?
You can. Actually, I was one of the first users of the HPC back in 2005. I was a grad student here at MSU, and I was one of the very first people to use it as a grad student, and I figured out how it worked, and I basically thread bombed the entire computer. It was awesome. My job, which should have taken 30 days to run, ran in about 2, but those 2 days, the system was running hot, they didn't know what the heck was going on, and the person in charge of the HPC calls me up saying, Dirk, don't do that. And then they called me up again later, and he said, Dirk, could you show us how you did that? And I still work with him now. But yeah, so you can break it. We make it really hard to break. Mostly what you can do is corrupt your home directory. It's like easy to break your home directory. That doesn't affect anybody else. If you nuke your home directory by doing a remove star or something like that, people do it. We can actually recover it. It has snapshots, but you won't be able to log in, and things will all act wonky and stuff like that. Yes, you can break it for yourself very easily. We do every once in a while have people do clever workflows which, saturate our network or something like that, and that can cause problems, in which case we smack their hand and say, stop doing that, show us what you're doing, and we'll help you do it the right way. You can also easily break things like installing your own software and not doing it correctly and stuff like that. But that's all personal stuff you do. You rarely, it's really hard to break it for other people. Although it's possible, it's just hard. Other questions? Yeah.
I have a question about, you mentioned you guys are focusing on workflows and enhancing workflows for the researchers, and that's a big thing that I think, I mean, for all of us, we want to develop something in a reasonable amount of time, right? So I was wondering, especially, let's say for LLMs, for fine-tuning an LLM, for example, is there suggested workflows already documented in your documentation of how to go about that?
So, no, but I'm working on that. If you have workflows, you want to work with me on those documentations. So there's different ways I can document workflows. One is I can do a tutorial. So here's a typical workflow. Here's what you would do. I don't have those tutorials, but I'm at that level where I can show someone, here's an example of what someone might want to do. It's harder to make a robust workflow that will work with lots of different people because everybody's doing it slightly different and it's not clear. But that's why I'm reaching out to all of the researchers on campus right now. I'm trying to build a working group of people that want to do these things so I can study what they want to do and identify what the reasonable time to spend on it. Once we get going, I'm hoping to build apps that will do like 90% of what you want. Like if you're fine-tuning, well, here's your training directory, here's your testing directory, just throw your data in and just hit go, and it will fine-tune a not model for you or something like that. I'm really close, I think, on that for RAGs, because LM Studio does a pretty good job with RAGs. Basically, we'll just designate a folder, you point to it, you run the trainer on it, and then you test out the resulted training thing. I'm getting close to that, but we're not there yet. Honestly, I can do it, but it's not doing it the first time that's easy. Doing it the 100th time is the hard part. Getting it into a robust workflow that works for a lot of people is hard. Yeah.
How do you think the most optimal training performance using computer? Like, what should I avoid doing? Like, from like good practices so I can get like the best.
We're actually working on that. We don't know. It depends on the libraries they use and how they do their underneath. I have had a student studying LM Studio that has this really cool, I forget what it's called, some sort of metric for determining how well it's learning. And that we've watched that, and if we give it more power, that number goes up. If we give it a lot more power, at some point it plateaus, and we know we've given it more than we need to, and so we can ask for less. And so there's no easy way to do that. I was hoping Hugging Face would tell us, here's the optimal machine to run it on. Hugging Face does not tell you that. They're used to working with people that have a machine, and that's, you get what you get, and you don't pitch a fit. We have the option of picking a machine, which is rare. And so we're trying to basically benchmark a bunch of workflows. That's part of what I'm trying to do to try to best optimize. But the way to do it is run small little examples at your different levels and see where it peaks out. And that's, unless someone discovers a way to do it, otherwise that's the only way I know it works.
What's like the best way to like make efficient use of the server in terms of like developing like let's say like code for something like that? Is it best to make it on your own PC and then upload it to the server, or develop on the server to ensure it compiles?
I almost do all my development on the server. It's pretty. We actually have, for those of you who care, we have a Visual Studio portal. So you can run through Visual Studio. It will connect to the HPC on the back end, and you can run your tests. Those are running on the dev nodes, so they're shared. So sometimes they'll run fast, sometimes they'll run slow because 100 people might be running at the same time as you, or one. When you schedule a job, you get all the resources that you ask for. So the stability, you don't want to benchmark on a dev node, basically. If you're running a test, you run it on a dev node, it really depends on who's on it at any one time and what they're doing. If you want to benchmark, you want to run it on the cluster.
I have a question.
Sure.
And I think it worked for me. So now since VS Code is implemented, what's the point of Jupyter? Because you can't run VS Jupyter style stuff.
Absolutely. Different people have different opinions. We try to be accommodating to everybody. People who are not comfortable with VS Code, Jupyter. I like Jupyter personally because I run on 3 different machines. and I don't want to set up VS Code in all the different machines. And one's a Mac, one's a Windows machine, and one's a Linux machine. So now I have to figure out how to set up VS Code to connect on all 3 different machines and get my settings all the same. Forget it. I'll just run a Jupyter node, and it makes me happy. So it's a choice of workflow. Anything that you think is the best, there's someone who's going to think it's the worst. And the only thing we can do is try to accommodate as many workflows as we
I
can.
thought there might be like some actual difference.
Nope.
Okay.
It's just a preference of opinion. Other questions? This is fun. What other slides do I have? Oh, there's me. Oh, this is the website where you can, where your advisor, your instructor, or me can request an account. You can also ask questions, but you will not be able to request an account from that website. Yeah.
Well, speaking of blockchain,
Yeah.
so I know you mentioned like mining section or whatever, but that's not the only. Say you want to create like a blockchain app,
Sure.
and you have heavy computational load, but you also want to test it outside of the system. Is it possible to do that?
What do you mean outside the system?
I'm not aware of HPCC allowing you to install ports.
No, absolutely not.
Yeah. So, like, it's not possible
Nope.
to do anything that's like interacting with outside.
Nope.
Okay.
That's actually a hard no.
Yeah.
A lot of people want to do that for a lot of good reasons, but the HPC security model absolutely will not allow it. If you're on the HPC, you can make a connection to the outside world, no problem. But the outside world hits a very hard firewall coming in. It's actually a multi-layered firewall. It really works hard to keep people out.
Would it be possible using VPN.MSU?
Probably not.
No?
Yeah, we don't want to expose ports externally.
Okay.
Because we store a lot of data that is highly sensitive, export controlled, other things. And it's yeah. We're actually having to lock down how we do it even more because the data protection rules have gotten more strict over the years.
Was there ever any consideration of creating like a separate
Yeah,
set
they're-
of clusters that are completely
Yeah, we actually have been talking about that quite a
so
bit.
they can be exposed
Sure.
and while keeping it private.
Absolutely. That has been talked about quite a bit. The problem is we'd need an influx of money. And that is available easily on cloud resources and stuff, where it's not, the type of security we provide is not available on cloud resources. And so when we get sets of money, they tend to want more compute nodes or more disk space in our secure zone from a university perspective instead of anything external. But I still see a need for that. We haven't gotten the funding for it. Yeah.
Training, taking data from like, let's say like, we're planning to make a game in Unity and taking and training like the model based on the game. Is it possible like, let's say like run like to like take training set and run it on the server from Unity? If that makes sense, like the game engine?
Sure. I haven't tried it, but theoretically it should. Honestly, where you as AI people would, like if you want a front-end interface, where the power here is you train on the back end. You train your models here in big batches where you have training and testing set and do all that. And then once you have a fully tuned model, you can then pull it out and it will run fast on. Usually models take a lot more power to train than they take to run. And so you use the HPC to do the expensive part, and then you can use your personal machines or whatever for the cheaper part. Yeah.
You guys were talking about things to take care of healthcare data leak at all from last year?
No, that was not our servers, and we didn't have much to do with that.
Okay. Are you helping with that now?
I don't think our team is, but they might be. We are part of, under the Vice President of Research, where that was under a different organization called IT Services. We are not part of IT Services. We do collaborate with them closely, but I don't know of anything we've done on that. We can share a data center. That's basically all.